Okay, so today I'm going to do something a little different, I think, and we'll just do a few computations, right? I mean, some of these computations you'll do a lot on homework and exercise classes and so on, but maybe it's useful if I sort of avoid them to not, otherwise you spend an hour doing calculations. But let's do a bit more computations, because I feel from some of the questions I receive, I feel like this might help give some understanding. Okay, so today we'll do a few computations, but I'll end with something surprising, I hope, at least. Okay, so let's sort of revisit the notion of path integral and integration over the complex numbers. Okay. Right, so we define things like, right, the integral of z dz, right, where this meant the path integral. This is sort of the same path integral as you see in multivariate real analysis, right? When you see things like, I don't know, like Green's theorem or Stokes' theorem or things like this is, if you go look, and I think you should, this is actually, it's the same definition of integral. Now, let's see, right? And so we consider the parameterization of the curve, right? We can right? We can think of a parameterization of the curve zt, let's say for t from A to B, is xt plus iyt. Right, we're parameterizing a curve on the plane, right? We do it over complex numbers, but really there's this identification that we keep doing in our heads, right? That right, I'll use some, I'm not saying exactly what, but there's clearly this identification between the complex numbers and the plane, and the real plane, that we keep doing, and it's very useful. So I try as much as possible to stay over C, but sometimes it is useful to go and think of things in terms of R2. Right, and of course, when you think about dz, right, the differential of z, right, and there's ways of talking about, differentials in ways that you can make algebraic operations with them. I'm not so interested in that. I'm more interested in thinking of this as, the thing that goes in the integral, and the calculations in the way that makes all that be compatible, right? Clearly, it should be, dx plus I dy, right? So let's see why this is the case, right? Why are we right? Let's see why is it that dz is actually equal to this, and in particular, right? If I were to replace here, I get an integral with right, two of these differentials summed, right? And some of the questions that arise was actually whether this what it meant for an integral to have two differentials and so on. So let's do a bit of calculations, okay, just to make all this a lot more clear. Okay. Okay, so what did we find this to be? So let's say we have a parameterization from A and B. So we define this A, B, f of ct, right, c prime t, right, dz dt, dt, right? And this is a normal integral over the reals. Okay, but of course, right, this is also equal to, right, I can think of, let's see how I should write. Right, so this is clearly equal to, I want to go up here. Let's see, what's the way that I can make this the most natural, right? F of right, and then what is z prime t? Then it's clear, it's just x prime plus y prime, right? So right? Okay, all I'm doing is grabbing the definition, right? This I'm not using. I'm more like using this type of argument to justify why this is how you should think about this. So this I'm not using. Okay, because it's not even quite clear what I mean by that, right? I'm just writing zt as its real and imaginary part and computing the integral. Right, but of course, if you see something like this, right, this is exactly the same thing as writing, right, integral over the curve of f of, right, x plus I, y, right? I'm stopping having the t's, right? Where x is just sort of the real part of gamma, y is the imaginary part of gamma, right, of the curve. And then clearly just dx plus I dy. Right? Because, right, if I were to now parameterize the curve, right, with x and y, when I am going to write this as an integral from a to b in the parameterization, I get exactly that, right? I get f of xt plus iy, and then here I get dx over dt, right? X prime t times dt, and I get I dy, which is over dt, which is exactly, right, I derivative of y dt. Okay, just to say that sort of this is all compatible, and in particular, oftentimes, right, there's this, maybe a little bit abuse of notation that sometimes we think of these functions, right, complex functions, as functions from the complex to the plane to the complex plane. Sometimes we think of it as functions from R2 to the complex plane, right? We can view this as a function from its real part and imaginary part, right? There's an identification here that, of course, is not the same object, right? This receives one complex number, this receives two real numbers, but even when we derive the Cauchy-Riemann equations, all this stuff, we sort of do this abuse of notation in which we, right, when there's no risk for confusion, we identify these two objects, right? So when we have a complex function and we sort of put two arguments, what we mean is sort of its real part and imaginary part. Okay, but now maybe let's do another calculation. Let me erase this part. And I think maybe this calculation will help see what is the meaning of dx and dy, right? And it's just when I parameterize the curve, right? It just means I take the derivative with respect to x, then dt, and then the derivative with respect to y, dy. But the way we defined, right, dx and dy was via the conjugate, right? We defined this dz conjugate because we were defining this in terms of things over the complex numbers, right? But all these definitions are equivalent. You can define them one way, prove that it's the same as the other. But let's say that I take, okay, so let's say that I take now f, right? Again, identified, right? By this I mean the identification of fx plus iy. Right, let's say that I take u xy plus I v xy. Right, and now I'm going to look at that integral. Right, okay, so maybe let me not try to use the fact that part of it is already on the board, otherwise I'm not going to have enough board space. See. Okay. Right, so this is now, right, I can view this as the integral of fxy. Right, and now, right, in exactly that language that we justified before. Okay, in the sense that if I parameterize the curve, what I do is I write my integral in terms of dt, where the dx dt is x prime and dy, right, dy dt is y prime. Okay, so let's see what we get. Okay, so now I'm going to keep things without parameterizations, right? And I get this u x y, right, plus I v x y. Right, now this times dx. Okay, maybe otherwise I won't have space. I won't expand for now. Okay, and now these objects, right? I mean, okay, there's an I here, but the integrals themselves, right? Once I can remove the I outside of the integral, there's nothing complex about them, right? This now becomes line integral over the reals. Okay, so let's collect the terms that don't have an I and the terms that have an I. Okay, so gamma, if I now collect the terms that don't have an I get uxy dx, and then the I squared becomes a -1, so there's no I, so I get minus that. So I get u, right, x, y dx minus v xy dy plus I integral of, right, and now I have to go get the other terms. So it should be this one against this one and this one against this one. So u xy d dy plus v. Oh, it fit. Good. Right? And so we could have defined, the complex. We could have defined complex integration in this way, right? If we were to start with just line integrals over the reals, right? And what this integral means, I mean, what I mean by this integral, right? You can write it integral. Usually, there's only one d, right? I could put another integral here, but really, by this, I just mean, right? Integrate this and integrate that and subtract the two, right? So of course, there's like a parenthesis. I mean, these are often not written, but of course, it's here. Okay. Okay, so just to say that, right, we define dx and dy maybe arguably not the most natural way, but it corresponds exactly to sort of the definition that would be natural, right? There's always a choice to be made on how to define things and what to then prove as consequences of that definition. Okay, is this clear? If anything is not clear, please interrupt. Okay, but I wanted to make sure, because line integrals are so important, I just want to be 100% sure that it's clear what is meant. But I highly recommend going and taking another look at Green's theorem and trying to make an exercise of trying to understand how, from the viewpoint of Green's theorem, what is with this story of integrals being invariant with respect to paths, and functions having exact differentials and things of this type, and Cauchy-Riemann equations. There's an interpretation for all of this in Green's theorem, that it's just another way of presenting the material, more real analysis based. It's not the approach we're taking, but it's worth spending a bit just thinking about that as a sort of completely different way of doing things. All right, so now that we've computed a little, let's answer the question that I posed the board last time. Okay, so when is it that, right, FZ dz is an exact differential? Okay, so what do I mean by this? Okay, so I'm going to use notation in complex numbers, but then we're going to transform everything over the reals, right? And we're going to do and answer this question over the reals and see what it means over the complex numbers. Okay, so today, sometimes I try to avoid this, but today I'm actually going to go back and forth between real and complex numbers, because I think in this thing it might help give intuition and understand what's going on. Okay, so basically, when is it that there exists, right, a function f, right, such that, in notation, it's not quite clear what is meant yet, right, because what it's meant by dfz is not completely obvious yet, equal to fz dz, right, very much like how we did when we were looking for, right, the exact differential. The p dx q plus q dy was the differential when it was equal to d big U. Okay, so let's go back to the reals, right, to answer this. Okay, so let's write fxy, right? Again, identification with f of x plus iy. maybe that's a bit difficult to read. I think this is probably the last time that we need to make this identification with the reals, actually. But I'm not 100% sure, but I think so. Okay, so, right, the identification with this. This is equal to some function, right? I'm calling u because it'll be, right, a primitive, clearly, right? Its derivative needs to be the function in some form. And we'll try to see exactly what form. Okay, so now, what is d of f? Okay, and for now I'll keep the x and y, right? But it's actually quite useful to take away the x and y because, then you don't even have to worry if you're identifying, with x, y as R2 or x plus iy because everything works out the same way, but I'll keep them for now. Okay, then what is this? This is just, right, the derivative. I need to take the differential here plus the one here, right? So it's the derivative of u with respect to x, right, at point xy, right, dx, right? Because if I was to parameterize against the curve, I would have to take the derivative of u with respect to x times the derivative of x with respect to t, right? That's what this little dx means, plus, right, now with y, so u x y dy, at point xi, sorry. Okay, it's just a lot more to write, plus I, right, derivative of v with respect to x dx plus I derivative of v with respect to y dy. Okay, so let's collect the x and dy terms. So we have derivative. Okay, I'll keep the x and y. This is all at point x and y plus derivative of v y v at x, of course. Sorry, I point x y. This dx, right, and then plus. Right, so derivative of u respect to y is y plus I okay, I think so far so good. Keep forgetting the xy. Okay, but now, right, so what is this? This is just, right, this is the derivative of f viewed as a, right, this is just the derivative of f with respect to x, right, because f is u plus iv, right, and this is also the derivative of f with respect to x, right? Okay. Right, here they're derivatives of real functions. Now I'm talking derivatives of complex functions, right? But the derivative is taken over a real variable. So the definition is exactly the same. Okay? Now I want to understand when is it that, right, that this derivative is equal to, right, the differential fz equals dz, right? When is it that, okay, let me maybe write another color. Right? When is it that this, let's say sharp is equal to fz dz? Okay, in other words, yeah, okay, so now I want to avoid having to expand everything out. But, yeah, okay, maybe I won't avoid expanding everything out. Okay, so then what is this? this is f, right? Or let's say that I wrote, yeah, okay, I'll just work out the calculations better. Okay, so f, right? I'll write as, let's say, of x and y, or of z, right? I'll write it with little u x y plus I v x y, right? These are small u's and small v's. These are big u's and big v's. Okay, maybe I need to make my v. Okay, all right. So now, maybe I'll make my v different. Okay, like this, just to make sure that we see it different. Okay, so then what is this? This is v, right? Now the identification with xy, right? This is u xy plus I v xy, right? dx plus I dy. Okay, so now we're asking, when is it that this is the same as that, right? So we have a bit to work out. Okay, but not so hard. We just have to do it. Right? Is it clear? If not clear, please interrupt. So maybe let's take a second. Right? So I'm asking, when is it that the function is an exact differential, right? fz dz is an exact differential. And I'm doing calculations by swapping back and forth between the complex numbers and the real numbers, just because it makes things, I think, easier to see. Okay? Maybe not easier to write, but I think easier to see, right? There's one way of convince you that all these things are compatible, that you can swap between the reals and the complex numbers, and that the complex integration is defined in a way that makes all this work. Okay, right? And basically, when we worked out those formulas, right, we essentially show that in this notation of differentiables, dz is equal to dx plus I dy, which is what makes all this work. Okay, so now we ask, when is it that this differential, right, is the same as this? Okay, so you already have here, I mean, the answer is already here screaming at us. We actually, like, technically speaking, we don't need to do any calculations now, right? The answer is already on the board, right? But maybe I'll still do some calculations because some redundancy is not bad. But why is the answer already on the board? Right? The answer is already on the board because here you get derivative of f with respect to x dx, right? This needs to be the same as this multiplied by dx. So this means in particular that, right, this already, if this is to be equal to that, it must be that the derivative of f with respect to x is equal to f, right? Let me see if I can write with another, right? This term here, right? Let's call it one exclamation point, right? Because it's the thing that shows up with the x needs to be exactly this. Right? Because otherwise these two expressions are not going to be the same. And whatever is in, right, the thing in the I, this term here, right? This term here in the I, let's say, okay, let's call it double exclamation point, right? What is it? Needs to be this term times I, right? So we immediately can get equations like, right? So let me write them here, right? Like integral of f with respect to x, where if you like things over the reals, this is just the derivative of u with respect to x plus I, derivative of v with respect to x, needs to be equal to f, right? And this one, again, derivative of f with respect to x, oh, not x, y, sorry. Okay, of course, y. Okay, derivative of f with respect to y, what does it need to be? It needs to be f times I, right? Because when I multiply f by I need to get the same thing on the dy. Okay, and the nice thing of using a notation which I don't put what's here is that I could either write this as a function of x and y, or write a function of z, or write a function of x plus y plus iy, and this is all true and all the same, right? The statements are exactly the same. Okay, so let me, right? So I guess there's two things I can do now. One thing I can like just match you, do all of this matching like big U and big V to small u and small v, but I think that's too much redundancy, right? Because it's obvious that you get partial of big U x plus I big V with x equals little u plus I little v, right? And the same thing here, right? So everything is very compactly written here. Okay. Now, what does this mean in particular? Right? This means in particular that the derivative, the partial derivative of f, oh, sorry, I keep swapping x with y. This is, of course, y, right? I'm getting this from the equation on dy. Now, what does this mean? This means the derivative of f with respect to x is equal to, right? So f, or I should say, maybe I'll write this the other way, is better, right? The derivative of f with respect to y is equal to I times the derivative of f with respect to x. Okay, so f needs to satisfy this property. Okay, but what is this property? Right, so let me write it again in another way. Okay, so what is this? I have that the integral of f with respect to y is equal to the integral I times, not the integral, sorry, the derivative of f with respect to x. Okay, so let's now expand this out again. So I get that integral, derivative of u with respect to y plus derivative plus I, derivative of v with respect to I equals I times derivative of u with respect to x plus derivative of v with respect to y. Okay, right? It's the same thing. Now we can collect terms, right? These u's and v's are all these u's and v's are all real. Oh, I think you're right. So okay, let's see. Let's take a step back. I mean, yeah, it's very easy to mistake an I for a 1 over I. So this term, this derivative of f with respect to y, right, needs to be okay. Let me write another equation. Right, this is equal to, right, f dx, right, where f I'm just identifying, right, is just u plus iv plus I f dy, right? I could have gone, of course, straight from this line to this line, right? Just from dz being dx plus I dy, I'm just putting this so that, you know, you could justify it if you wanted with a few more calculations, right? Okay, so we have this. So then this term needs to be equal to f, and this term needs to be equal to if. Agreed, right? So double exclamation mark needs to be equal to if, and it is exactly what I have here. Right? Okay. All right. Thank you. Okay. Now, there was a question about yellow. I guess, sorry, that's gone. I've erased all my yellow. So hopefully there wasn't a mistake. Now let's see what there's a problem here. Yes, there is an I missing here. Okay. Any more questions or? All right. Okay. So now let's work this out. Let's just match terms, right? Let's match real terms. We have that partial of u with respect to y is equal to minus partial of v. There is an issue here for sure. This is x. I keep swapping the x's and the y's, sorry. Okay, so partial of u with respect to y equals partial of v minus partial of v with respect to x, and partial of v with respect to y equals partial of u with respect to x. Right? And now in this form, you may recognize them as the Cauchy-Riemann equations. Right? So it's all going full circle. Okay? And in particular, oftentimes the Cauchy-Riemann equations are just written like this. Right? I don't remember now if we did that at the time, but right, it's just the same thing, right? Because when two complex numbers are the same, you just get right, the real part and the imaginary part need to be the same, and this is just the equation you get from real and imaginary parts having to be the same. Okay, so what does this mean? Right, this means, and we saw this before, that actually big F is analytic, right? Because it satisfies the Cauchy-Riemann equations. Right? It needs to be differentiable in the complex analysis sense. Right? So the function f right, and in particular, right, f of z is equal to the partial of f with respect to x point z, right? But if a function is analytic, the derivative with respect to x is just its derivative, right? So this is just the derivative from the complex analysis derivative. Okay, so in particular, we get a theorem, right? So theorem. Okay, let's say that we have a region. Right, f continues in the region, right? Just because I want to be able to take integrals and not have to worry about things. Well, let's say this continues in the region. Then the integral over a path of fz dz, right? Right, we know that fz dz being exact differential is equivalent to the paths, to the integrals over paths depending only on the endpoints. And now we showed that fz dz is an exact differentiable if and only if there is a function, right, whose partials match f. So we already knew that, but we just realized that for the partials to match f, in complex analysis, we actually need f to be analytic from the complex analysis sense. And so this means that for a region with f, a continuous function in the region, then this integral depends only on the endpoints of gamma, right? Depends only on endpoints of gamma, right? If and only if f has a primitive in the region, right? Whereby a primitive, I mean a function f from the region to the complex numbers, such that the derivative in the complex analysis sense is equal to the function. Okay, this makes sense, right? Because it doesn't feel like yet that useful of a theorem, to be honest, right? Because how are you going to tell if a function has a primitive, right? It's not completely clear yet. But it makes intuitive sense, right? The integral depends only on the endpoints if there is a primitive, because then it should correspond to the integral at the end of the curve minus the integral at the beginning of the curve, right? And therefore, it depends only on the endpoints. Okay, so now there's two things we can do. We can see an example. Okay, so maybe I don't have time. I want to show you already now a cool application of this. So I'll skip the example, but I highly recommend just sitting down and trying the example fz equals z. Okay, so to get intuition, I highly recommend just example, right? Just try f of z equals z, right, over some curve, and check, is this right? So, and ask yourself, is z dz an exact differentiable? Is. Okay, and work this out because it's a relatively simple example, both from the side of complex analysis and from the side of real analysis and just line integrals over real analysis. So like, try to answer this question using sort of the different ways of thinking about path integrals. And I think in doing so, you'll get a good intuition about why they're all the same and a better sort of grasp of what's going on with complex integration. Okay, I mean, for me to do it on the board, I'm not sure it's as useful as you just trying it. And it would take me probably like 15 minutes, or at least 10. And I want to show you already now a cool application of this. Okay, so now let's say that this is let's say that we have a curve, right? So let's say this is a closed curve, right? My curves are always differentiable and regular, right? But let's say we have a closed curve, right, in C, of course. And now let's say that I take the integral of z minus a to the n dz over this curve. Okay, and let's say that n is non-negative. Okay, what does my theorem tell me? Okay, any volunteers to answer? Right, this feels, I mean, the curve could be quite nasty, right? I mean, think of the curve as, right, maybe let's take an example. Let's take this being 0, or a, say, and now take a curve that does this. Okay, let's take this as my curve for the sake of this discussion now, right? And okay, so someone mentioned a being inside the curve. Let's make this a. Right, there's clearly something special about a, and there's nothing special about 0. So let's make this point be a. Let me undraw the axis. Okay, this is a point A. Okay, and the axis, say, is over here. It doesn't matter. Okay. Okay, so why is the integral? Someone says 0 if a is not inside the curve. What does it mean to be inside the curve, or what's the issue with being inside the curve? Right? Z minus a to the n is a primitive, right? Z minus a to the n is the derivative of, right? We know how to differentiate polynomials over the complex number, is the derivative of z minus a n plus 1 over n plus 1. Right? And this function, right? This function is analytic on the whole complex plane, right? It's a nice polynomial. Okay, so let's see. I really want to show you something cool today, so I'll try to do it in the last 5 minutes. Okay, does everyone agree with this? Right? And this is analytic, right? And z minus a to the n plus 1 over n plus 1 is analytic in all of C. Great. So we get immediately the theorem that this is equal to 0. I mean, if you think about this for a second, right, because it only depends on the endpoints, the curve is closed, so it needs to be equal to 0. If you think about this, this is already quite remarkable that one can do things of this type, right? And in fact, by drawing the right curves, you can compute integrals over the reals that before were very difficult to do using this theorem, essentially. Okay, I mean, the theorem will have to get a little bit better, right? We have to understand really well when f has primitives or not, but we'll get there. Okay, let's make things a little more complicated. What if n is, right? What if n is equal to -2? What happens then? Or, or n smaller or equal than -2, even. Right? Let's say that n is equal to -2, then it also has a primitive. Right? Because, say, for n equals -2, then z minus a, right, is the derivative of, so n plus 1 minus 1, of -1 over z minus a. Right? And this is, well, it's single valued, right? It's analytic and single valued. Right? There's no like issues like with square roots or anything like this in C not containing A. Right? So as long as A doesn't touch the curve, right? If A was here on the curve, there would be a problem. But right? Because I mean, at some point you're dividing by 0. But if A doesn't touch the curve, then it's still fine. And of course, I did it here for n equals -2, but n smaller than -2 also, of course, has right. I mean, the formula is the same, right, as an antiderivative. Okay. Now for the cool thing in the last 2 minutes, what happens for n equals to -1? And this is key. This is a key feature of complex integration, complex analysis. Right? What happens when n is equal to -1? Right? It also has a primitive, right? We can take the log, but the log is not clear that we can define it single valued. Right? Because the log, part of the log is the argument, which is the angle, which is when I rotate, I go from 2 pi back to 0. Okay, so let's do an experiment. Let's take C, the circle, around A, right? Parameterized this way, Z of t equals A plus R EIT. And now let's take the integral over C of 1 over, or let's say dz, over Z minus A. Right, by this I just mean 1 and dz here is the same. Right, and what is this equal to? Okay, so because I don't want to keep anyone past the hour, we'll do this on Tuesday, but just try to do this calculation. Okay, and what comes out of this calculation, the conclusions are a key feature of integration complex analysis. I don't want to keep anyone longer than the class time, so we'll just do this on Tuesday. Okay, but hopefully the calculations and the swapping from reals to complex helps give some intuition of what complex integration is. And then I think once we're past this, then right, I don't think we have to go back to the reals anymore, probably. And but it's good to, it's important to do it once and swapping between the two, just to get a better feel of how it relates to things like Green's theorem and so on, right? And path integrals over the reals. Okay, I'll be around for a bit longer. If anyone has questions, please just stick around and ask. All right, thanks.